Iron sights. Iron sights have been around since the first arquebuses of the 16th century and work on 2 points: a front post near the muzzle and a rear notch near the shooter. No battery, no electronics, nothing to break except the metal itself. The moment you bring up any other sight in a conversation, some old-timer materializes and says he had to hit targets at 500 yards, standing with iron sights in the army. Every time, without fail. The problem with iron sights is biological. The eye cannot focus on 3 separate points at different distances at the same time. You focus on the front post, the target blurs. You focus on the target, the post goes soft. You're always sacrificing something. The aperture sight was the fix. Replace the open rear notch with a ring and a small hole in the center. The eye looks through the hole and automatically centers the front post without conscious effort. 2 focal planes instead of 3. The M1 Garand, the Lee Enfield variants from 1941, and the M16 all use this system. The ghost ring is a variation with the rear ring made so thin the eye practically ignores it. Faster at close range, less precise at distance. Iron needs no battery and is nearly indestructible. That's why every modern firearm still ships with iron sights as a backup. Red dot sight. In 1974, a Swedish engineer noticed that a point of light reflected off a curved mirror appears in the same position in the field of view, regardless of where your eye sits behind it. In February 1975, Aimpoint AB launched the world's first commercial electronic red dot. The mechanism is clean. An LED emits light toward a curved mirror with a coating that reflects only that specific wavelength. The result is a dot aligned with the barrel axis floating in your field of view. You put the dot on the target and shoot. No front post, no rear notch, no conscious alignment. The practical difference is significant. Both eyes open, close range, you acquire faster than any iron sight setup. The dot doesn't care about your cheek weld or your exact head position. It stays where it is. That consistency is why militaries and law enforcement made the switch and never came back. Holographic sight. EOTech introduced the first holographic weapon sight in 1996. The technology comes from laser holography research and military aircraft heads-up displays. Fighter jet targeting miniaturized and bolted to a rifle. Not a comparison. Literally the same underlying research. The mechanism is entirely different from a red dot. A hologram of the reticle is recorded directly into optical film embedded in the sight's glass at the time of manufacture. When an internal laser illuminates that film, light diffraction reconstructs the full reticle image, which appears to float in the field of view. No reflective mirror involved. That difference has one consequence that matters more than anything else. If 90% of the glass is blocked by mud or shattered from impact, any surviving fragment of the hologram still contains the complete image. The reticle still appears. That's how holograms work. Destroy part of one, and the remaining pieces still show the whole picture. Block a red dot's mirror, and the dot disappears entirely. The EOTech reticle gives you 2 modes built into one. A large outer circle for rapid target acquisition at close range. Put the threat inside the circle and shoot. A small center dot for deliberate shots at greater distance. One sight, 2 ways to use it. Glenn Binden developed the ACOG at Trijicon in 1986 using prisms instead of conventional lenses. The same fundamental technology as binoculars, achieving real optical magnification in a body compact enough for actual combat use. The standard military model offers fixed 4 power. The reticle is illuminated by fiber optics during the day and tritium at night. No battery required. Tritium is a radioactive isotope of hydrogen that emits light as it decays, a process that lasts 10 to 15 years before needing replacement. It is probably the only sight in the world with a nuclear expiration date. The limitation showed up in urban combat. 4 power is too much when the engagement is happening at 10 meters inside a building. You're staring at a blurry torso filling the entire field of view. Special operations troops started mounting red dots on top of their ACOGs for fast transitions. When your own users are strapping competing products on top of your product, the message is hard to ignore. Trijicon eventually incorporated it as an official factory option. Telescopic scope. A series of lenses inside a tube magnifies the target image out to distances where any other sight becomes useless. Elevation and windage turrets adjust for bullet drop and wind. On precision scopes, each click moves point of impact roughly 7.3 millimeters at 100 meters. A cheap scope tells you that you adjusted 10 clicks. The bullet lands wherever it wants. These are not the same product. Variable magnification is the modern standard. A 3 to 9 power goes from 3 times to 9 depending on where you set the ring. The trade-off scales with the number. More magnification, smaller field of view, stricter eye placement requirements. At 20 power, move your eye a few millimeters outside the eye box and the image vanishes completely. What most people don't understand about high magnification shooting is that you are not looking directly at the target. You are aiming at a reticle suspended in optical space. At 25 power, heat rising off the ground makes the target shimmer. Move your eye 2 millimeters and the reticle appears to drift. Those millimeters translate to a complete miss at 800 meters. The image looks sharp. You shoot with confidence. The round goes wide and you stare at the scope like it personally betrayed you. It did. That phenomenon is called parallax, and it exists in every scope. Correcting it requires a specific adjustment dialed to the exact distance of your target. LPVO. The low-power variable optic exists because no fixed magnification sight works well at both 10 meters and 400. A variable optic that starts at 1 power, meaning no magnification, both eyes open, exactly like a red dot, and goes up to 6, 8, or 10 times depending on the model. At 1 power, you run it like a reflex sight. At 6 power, you're engaging targets a red dot can't resolve. One twist of the ring makes the transition. The concept sounds obvious in retrospect. The execution took decades because manufacturing lenses that hold consistent optical quality across that full magnification range is extraordinarily difficult and expensive. Cheap versions fail at both ends. Good ones cost accordingly. The U.S. Army's next-generation squad weapon program selected the Vortex Razor HD Gen 3 1-10 power for the new XM7 and XM250. That's the institutional endorsement that ends the debate. Laser sight. The concept is the simplest of anything on this list and the most dependent on conditions. Project a dot onto the target. Shoot where the dot lands. No alignment, no cheek weld, no eye box. A child understands the mechanics in under 5 seconds. The problem is physics. Visible green lasers are today's tactical standard. The human eye detects green more easily than red across a wider range of lighting, which makes the dot more visible in varied conditions. But in intense daylight beyond close range, the dot competes with ambient light and loses. The most intuitive sight system available becomes unreliable in the most common outdoor environment. Infrared lasers solve this by being completely invisible to the naked eye and appearing clearly through night vision devices. Special operations forces pair IR lasers with night vision to shoot from unconventional positions without revealing their location. The target sees nothing. The side with the equipment sees everything. The technological gap between those two positions in that scenario is difficult to fully appreciate without witnessing it directly. It is the fastest sight in theory and the most condition-dependent in practice. No other system has that kind of distance between concept and real-world limitation. Night vision and thermal. Night vision amplifies available ambient light through an image intensifier tube. Moonlight, starlight, residual glow from a distant city. The image is monochromatic green because the human eye distinguishes more shades of green than any other color. Generation 1, 2, and 3 define tube quality and low light performance. Gen 3 is the American military standard, and the difference between a Gen 1 tube and a Gen 3 in minimal light is not an incremental upgrade. It is a different category of device. Thermal operates on entirely different physics. Every object above absolute zero emits infrared radiation. Thermal imaging detects temperature differences and converts them into contrast. A warm target against a cold background appears clearly regardless of light conditions, rain, smoke, or camouflage. Camouflage breaks up a visual pattern. It does nothing about heat. This was scientifically explained in Predator. The military had already understood it for considerably longer. Those two technologies together represent the actual ceiling of what a sight system can achieve. Not just seeing in darkness, but seeing through conditions where darkness is the least of your problems. The progression from a front post and a rear notch to a thermal sensor detecting body heat reads like a long distance to travel. It is 500 years of the same problem being handed to better engineers with better tools every generation. The sight changed. The question never did. We've covered everything from the most basic iron sights to the most advanced thermal systems. Now the question is yours. Which sight system do you run, or which one do you want to get your hands on? Drop it in the comments. Thanks for watching. See you next time.